Okay, so welcome back to another video. So here today we have a following verification that we want to show, and it's that if we're given the results that the double integral of e to the negative x of times y times sine of x dx dy is equal to the same thing, but except the differentials are different, the order of integration is different, so dy dx, we want to show that the improper integral from 0 to infinity of sine of x dx is equal to pi over 2. And so this integral, this evaluation over here has a special name. This is actually known as the Dirichlet Integral. And there's actually several ways to actually prove this evaluation. So I'm actually proving one of them, one of the many for today, and specifically it's dealing with the double integrals. There's other ways to calculate the following over here is you can actually use the Laplace transformation using, the sine of t function. You could also use the differentiation under Feynman's trick. Another way you could use is, with complex integration. And this one's an interesting one. You can actually use the Dirichlet kernel, which if I check this out, Dirichlet kernel is actually, it's a collection of functions specifically for d sub n of x is equal to 1 over 2 pi times the partial sum from negative n to positive n of e to the I times k times x. I is an imaginary unit that says that it's equal to 1 divided by 2 pi, then times 1 plus 2 times the partial sum of cosine of kx. Then if you evaluate that is actually equal to sine of n plus 1 over 2x, and then divided by 2 pi times sine of x over 2 for n is some non-negative integer. So you can actually use that. I don't know too much about Dirichlet kernels, but you can actually research that yourself if you want. I'm not that too familiar or versed about that sort of definition. But that is one way to actually prove the Dirichlet integral in its terms of evaluation. Another sense, or rather, some interesting things to note about the Dirichlet integral is more of the lines that it's not absolutely convergent, so the absolute value of your series of sine of x over x, that's actually not Lebesgue integrable, and so that would mean the Dirichlet integral is not is undefined in the sense of Lebesgue integration. It also can be used for using Dirichlet's test for improper integrals, so that's another thing that is very helpful and handy. But I'm just rambling too long going on, so because basically I just want to use today's video is basically just showing that the verification with the results here actually comes down to the final evaluation that the Dirichlet integral is indeed equal to pi over 2. So I think the results speak for itself, rather, the methods that I'm going to show, so I don't really want to put too many things out there. I just want to give the facts about Dirichlet integrals in general. But how about we just jump in and see where this can take us from this step to this step. Okay, so let's suppose that, let's say the right hand side, so I'll put RHS, we're going to set that equal to the integral, the double integral, so they share the same bounds. So e negative x times y then times sine of x dy dx. There's a little bit of space here. Let me actually just fix that up a bit. This is actually a little bit easier to solve, or we're not really exactly solving, but more in the sense that we want to simplify this down a little bit to get the following results for what we want to show. How about we'll focus on the inner integration. So we'll integrate from 0 to infinity in terms of y. So here we're going to start with the integral from 0 to infinity e negative x times y sine of x, and then dy. Neat thing is that this is in respect to y, so sine of x in this sense is actually just a constant, so I'll just move that outside of our integral. So 0, infinity, and then e to negative x and y, and then dy. So what you can do is you can actually perform a u-substitution with the in respect with partial differentiation. So I suppose I could say that u is equal to negative x, y, then du is equal to, so now that would be negative x and then times dy. So now if I just perform the substitution, so of course negative x is just outside. So yeah, so rather I'll just write it like this. So I can say that negative sine of x and then divided by x. Then we have our integral let me just leave the bounds empty for now. So this will just be e to the u and then du. And so this is equal to negative sine of x and then divided by x. Then we integrate, then e of u is just e of u. So just put that back in. So negative x, y, evaluate from infinity to 0. Then you'll see that negative sine x and then divided by x. We plug in infinity over here. So that's just going to be 0. So it's just going to be 0 over here. And then if we plug 0 over here, then that's just going to be 1. So 0 minus 1 is 1. That's a negative. So therefore we have that this is just sine of x over x. And so what we can conclude so far to say is that now the right hand side, so far we have simplified to say that this is just equal to the improper integral of sine of x and then divided by x dx. Okay, so we've gotten that far. So that's pretty awesome, because we see that we want to show that sine of x over x is equal to pi over 2. So that actually just leaves one side that we have already simplified down, so we can just stop from here. And so we have shown the right hand side is equal to this, simplified down, and now we just have to deal with something with the left hand side. So let's actually take care of that. So now the left hand side, so over here, so I'll put the LHS that's equal to the double integral 0 infinity and then 0 infinity e to the negative x times y and then sine of x dx dy, right? So we're going to use the same method again. We're actually going to deal with the integration. So just like from before, so we're only focusing on the inner part. So in this case now we would actually have to integrate in respect to x. So here negative x, y, and then sine of x dx. Now if you want to, you can actually perform do some integration by parts, but I think preferably there's actually an interesting, well, yeah, I prefer to say interesting. You could say I just got a little bored, so I try to make things a little interesting. When I say this, you'll notice that sine of x, we can actually write this in terms of the polar form in the complex world. That's just equal to the imaginary part of e up to the ix, so the imaginary part of Euler's formula. So in other words, we're just taking the imaginary part of this entire improper integral. So now we have the following like so. E to the negative xy, then times e to the ix, but let's actually just add the exponents together with that rule. Then from here, you can actually perform some, yet again, another u-substitution. So now, this case, I'll let u equals, our exponent. U equals negative x, y, then add this with ix, then du. So differentiate in respect to x. So now this will just be negative y, and then add this with I, and then dx. So now we actually just plug in our substitution. And if I just skip, the integration, so we're going to have the following value. So well, we need to calculate it at least. So the imaginary part of, so I can factor out a negative from here. So this will be negative. And then this is, we have e to the power y, or negative x times y, add this with ix, and then divide it by. So I factor out the negative, so now this over in the denominator would be y, and then subtract I. And then we just integrate, and then we evaluate from 0 to infinity. Or if you want to, we can actually fix this up a little bit and actually factor out the negative x from here. So now e, or negative e, then negative x multiplied with y, and then minus I, then divided by y minus I, 0 to infinity. We just keep going. Let's see. You plug infinity for here, then that's just going to become 0. And if we plug 0 for here, then it's going to be 1. Or I mean, if we plug 0 for x, then the numerator is going to be just 1. And well, 0 then minus 1, then that means that would become a positive. So it's the imaginary of 1 divided by y minus I. So that's kind of a little bit difficult to proceed from here, but it's actually not exactly that difficult. You can actually, because there's a negative I on the bottom, when you're dealing with complex numbers, you don't want the imaginary u to be in the denominator. So you can actually just multiply its conjugate from both the top and bottom. you'll see that by doing so over on the top is y plus I, and then y subtract I, then times y plus I. We see that we can get that this is the imaginary unit of y plus I, then divided by, so due to FOIL, so it's just y squared. And then this is difference of squares, actually, you see over here. Negative I plus I, that's negative I squared. In other words, that's just plus 1. And then if you actually just set the imaginary unit, then that means it's actually just equal to 1 divided by y squared plus 1. So we can come to the conclusion and say that the left-hand side, so far we have shown that this is actually just equal to the improper integral from 0 to infinity of 1 divided by y squared plus 1 dy. But that's easy antiderivative to see that that's just actually just arctangent of y. And then evaluate this from infinity to 0. Simple computation over here. Let me fix that up for a sec. That's simple from here because, you know, arctan of infinity is actually just pi over 2. And then subtract 0 for here, so that's 0, so therefore it's just pi over 2. So therefore we can say the conclusion is that we have the left-hand side equal to the right-hand side. This is the right-hand side, and then this is the left-hand side. And so therefore we can see that indeed, well, I'll put it like this. We'll say we said that the left-hand side is equal to right-hand side. And so therefore we have shown that the integral from 0 to infinity of sine of x dx is indeed just equal to pi over 2. And just like that, we have just verified the following as necessary with the given results, just like that with the double integral. So yeah, that's pretty cool if you ask me.